Süper. Hı hı. Ha, ha, gördüm. 1, 2, 3. Ha, normal. Ha. Baland bo'lib ketadi, shovqin bo'ladi. Bunday. Ha. 1, 2, 3, 4, 5. Ha, yo'q, anavi ozgina qattiqroq gapiradigan bo'lsam. Ha. Tushundim. 1, 2, 3, 4, 5. Mhm. Endi o'rganib olar ekanmiz. Yo'q. Aha. Bo'ldi. Qanaqa chiqadi? Ha, keyin. Ha, xudo xolasa. Ha, men mikrofonniki. Qancha ketadi o'zi? Ha. Ha. Ha, oddiy bir nimadan tushadi? Ha. Hozir ketyaptimi yozuv? Zapis? Qanday to'xtataman keyin? Tugagandan keyin. Ha. Остановить трансляцию. Остановить. Aha. Zapisi. Men o'taman-da. Ketma-ket men o'taman. 3 ta bor. Bir xil. Ha. Ha, bu translyatsiya ham o'chadi. Ha. Aha, tushundim. Ha. Aha. Bo'ldi. Aha. Bo'ldi. O'sha YouTube'dagi. Mhm. Ha. Ha, va bir vaqt o'zida. Tushundim. Hammasida. Mana shu yoqda oladi doskani. Ha. Ekran zapis bo'lmaydi. Doska полный zapis. Sog' bo'ling. Ha, mayli. Bo'ldi. Ha. Yo, mana bittaga yetar. Bitta. Ha, bir. Yo'q, nimaga? Bir xilda. Bitta anavi bir xilda. Mavzu ham bir xil. Keyin bu guruh aktivligi yuqoriroq. Ular sertifika qilinmaganda kuchlilar uchun. Ha. Hmm. Bittasi tanladi. Ha. Hmm. 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 To'g'ri. Ha. Zapis. Hmm. Ha, to'g'ri. O'rgandim. To'g'ri. Savol tug'ilmaydi ichida. Sog' bo'ling. Ha, bo'pti. Ha, mayli. Ha. o'tira olamiz. Bo'ldi. Yaxshi, rahmat. Ol. Ha? Pilotlarga. Da. Okay. Alpha. So, today we'll continue the chapter 14. So the second part, the first section is RL circuits. So RL circuits. So what's R? Remember? Resistance. So this is R. What's L? Yeah. Self-inductance. Yeah. So L. Self-inductance. Yeah. So in this section, so can you see the figure? The figure A. Figure A. So it consists of the self-inductance, inductor, and resistor, and power supply, and two switches. Yeah. So if I call the first switch, we'll have this circuit. Yeah. So this is open. That's why the current flow in this direction, I. So this is why we have this circuit. So if instead of the if I change the but S1 switch 1 by switch 2, so we'll have this circuit. Yeah, this is open. So that's why. So there is no the current, the flowing. So that's why we have only this circuit. So this circuit consists of R and L. Yeah. So we will write equations for each one circuits. Yeah. The first one. So do you remember the integral E dot dl equals to what? Chemical ish. Oh no. So it was 0, right? Do you remember? So this equation for the general circuits. So we use this uh, integration of dot product for Kirchhoff rules. Yeah. But so here we have uh, inductance. So inductance to create induced EMF, right? So that's why. So dphi dt. Yeah. So so what this product gives us? So the current flow in this direction, I. Yeah. So so uh, inductor has no the resistance. It's like superconductor. Yeah. So this is why. So the magnetic electric field inside the inductor inside the inductor is E is 0, right? So electric field on resistor is this direction. So electric field inside the power supply is so this direction, because electric field so directed toward from positive to negative. Yeah. So this is why the first one is positive terminal, and this is negative terminal, right? So this is why. So electric field from plus to minus, yeah? So, so the left side will be equals to, so the current flow in this direction. That's why E, so E is the EMF of the power supply minus, so the power the voltage drop of the uh, inductor is 0 minus, so the R1, so the R is I times R equals to, so the minus L di dt, right? You agree? So I just substituted here df dt by L di dt. So do you remember the yeah? What? So the dot product of, so EDL is equals to minus dphi dt. Yeah. So where is exit? Okay. So integral of dot product of EDL is equals to what? Potential difference. So we are integrating potential difference of each element. So how many elements here? So the power supply, so E, and inductance, so inductor, resistance, yeah. So inductor is, there is no the resistance, so that's why current times, so the potential difference is I times R, right? So if I want to find the voltage drop of the inductor, so I need to use here current times, so the resistance of this inductor, yeah. So I said that before, the resistance is 0, that's why the voltage drop is 0. And the first one is current flow in this direction, so the E minus, so 0, instead of I'm using here VL 0, minus, so the voltage drop of the resistor is I times R, right? And this equals to, so minus df dt, right? Yeah. So magnetic flux is can be found by L and I, right? If I substitute here, so flux by Li, so L is constant. It depends on the geometry of the inductor. So the so so the variable here current. So this is why. So E minus ER plus, so df dt, right? So I just I'm bringing this expression the left side, just minus to plus. So E minus E I R minus, so if I substitute here F flux by L I L, so the plus here, d I dt, right? Is 0. Yeah. Or so dt plus E, so the minus I R and plus E is 0. So this is the differential equation. So if I solve this differential equation, I will have the current, so the changing of the current as a function of time, yeah, because here is the current depends on time. You see here derivative of current. Yeah. So solution of this differential equation is I t is IT is E divided by R. You preface to the 1 minus, so exponential minus R T divided by, so self-inductance, yeah, or, so here is R1 minus uh, E powered by minus T divided by tau, yeah, and what? Reversal. So RL divided by, so I think here is a mistake, because, so if tau in the index is L, yeah, so it's not the self-inductance. Tau is indexed by the L, okay, so tau is, tau L is L divided by R. This is time, so inductive time constant, okay, because, so uh, because here is, so the L is constant, yeah, and R is constant. So the division of the, or ratio of this constants, I can write so I can symbol by another the constant, which call it inductive time constant. Okay. So this is current. So the current is a function of time. So if I draw the graph of the current, let me draw. So imagine we don't have a L in our circuit. We just have only resistance. So E, R, yeah. So current flow in this direction. So if I draw the time dependence of the current, so what do we have? No. What? So a constant line, because the current is here, so the E divided by R, right? So so I consider that the internal resistance is 0. Yeah. So it's from the Ohm's law, yeah. So if I add here at the circuit the inductor L, so when the current is flowing in this direction, so the inductor is fight against the current. So the inductance, so the try to stop the current. So this is why, so current, so the from 0 to, yeah, so reach the maximum value after some time. Yeah. Okay. So when, question here, when, so the current reach the maximum value. So no, so look at here this equation. Current, so maximum current is equals to E divided by R, yeah. So if the current maximum value is equals to E divided by R, so it means that this expression is equals to 1. So it means that 1 minus 0, right? So E powered by minus T divided by tau is 0, right? So minus T divided by T L is equals to what? 1, right? So 1 over E T divided by L is 0, right? So this division is equals to approaches 0 when this function approaches to the infinitive, yeah? So it means that T divided by, so what? Tau. So this approaches to what? Okay. Let me just write, so tau by, so T equals to tau, yeah? So T equals to tau, yeah? If I substitute here, so T by tau, so I'll have E divided by R, so 1 minus E forward by minus 1, right? So this is, so E divided by R, so the 1 minus 1 over E, yeah? It's, so this equals to 1 minus 1 over E, approximately 0.64. So it means that if the after time equals to inductive time constant, so the current reaches to 64% of the maximum value. Okay. So what about EMF voltage? So the VL is equals to dv dt, right? Or L di dt, right? Yeah. So in this graph, you can see the EMF as a function of time. So here is the current is increasing. So the EMF is decreasing. Yeah. When we describe this circuit. Yeah, look. So current flowing this direction. If I have inductors, yeah. So inertially, so the EMF is existed when only the magnetic flux is changed. Here is current, so the fight against current to the of the power supply. So this is why, so we can see the producing the EMF, induced EMF. So, but after some time, this equals to it reaches to the 0. So look here. So we have this circuit. So not the circuit. So without power supply. So this circuit consists of only resistance and inductor. So this is why this graph is from E to 0. Okay? Because uh, when I close this switch and open this switch, So we don't have an external power supply. Yeah. So but we have induced EMF because so the if I disconnect the power supply, so it starts to the stopping current flowing from the power supply. So it means that current is decreasing. Decreasing of the current is leads to formation of induced EMF, d/dt. Yeah. So this is why. So so we don't have power supply here. So but sometimes we have current in this circuit. Yeah. So this current is or voltage drops. So but it takes some time. So so this time is so the by so it's a function of time. So the E so decreasing so damping voltage. Yeah. Okay? So this graph of this voltage. So if I uh, if I switch the power supply, we'll have this graph. If I disconnect the power supply, I'll have this graph. Okay. So we know the uh, magnetic field energy. So do you remember? U equals to 1 over 2 Li squared. So here is equations for the voltage as a function of time. So so the graph. So you see the above that. So the expressed by this equation. Okay. So exponential graph. So and the problem. So the example here. So in the circuit, the figure uh, 14.12 here. E equals to 2 volts. R equals to 4 ohms, and inductance is 4 Henry. So the when is S1 is closed and S2 is open. Yeah. So the figure before we see. Um, so question here. So what's time constant of circuit? So the time constant is so what's it? Tau. Tau is equals to what? L divided by R. So we have L. So and we have R. So time constant equals to what? 1. So so it's simple, yeah. So next question. So what are current in circuit and the magnitude of the induced EMF across the inductor at time t is 0 and time is 2 times the larger than time constant, and as t approaches to the infinity. Okay. So here is the first one solution, and and so we have current equation here. So the question B was so t equals what? 0, right? So I'm gonna substitute here t by 0 from this equation. So I instead of t 0 second here is equals to so E divided by R. So the 1 minus E forwarded by uh, instead of t, and so tau is what? 1. Yeah. So it's 0. Doesn't depend on the power supply or resistance because so this expression is 0. Okay. So 0 ampere. Okay. So it's known from the graph. Yeah. If you have inductor, so So the current starts increasing from 0, right? So here is time is 0. So that's why current is 0. So what's the 31? T is equals to double tau, yeah? So I instead of T is 2 seconds, yeah? And is E divided by R and 1 over 1 minus E times, so 2 divided by 1, right? And this is so so what was the EMF? EMF of power supply? So 2 volts, yeah? 2 volts, R is 4. So 2 divided by 4 and 1 minus, uh, so it's 1 over E squared. So 1 over 2 E. So E powered by E powered by minus 2 is equals to 1 over E squared, right? So that's why. So what we have? So 0.5, 1 minus, so it's so 2.7 square. Yeah. Can you compute it? So or we have here the answer, yeah. So it's yeah, no. So it's so 0.5 times 0.86 is equals to 0.43 amperes. So this is question B, yeah? Yeah. Okay. So what about the time is approach to infinity? So I, so time is approach to infinity is E divided by R, 1 minus, so the E powered by minus T divided by tau, right? So it's, so okay, E powered by T minus tau is equals to 1 over E T divided by tau, right? So if the tau approaches to the infinity, so it means that it's approach to the 1 over infinity. This is approach 0, right? So this is why, so the current, so there can be E divided by R, because this is goes to 0, and we have only E, so this division, yeah. So the 2 divided by 4, right? 0.5 ampere. Okay. So it's known from this graph. So if time to approach to the infinity, so the current reaches the so the maximum value. Okay. Any question? No? So oscillation in LS circuits. LC. So the circuit consists of inductor and capacitor. So okay, can I clear the bar? Can I clear bar? Yeah. Oscillation is different. capacitor and inductor. So this is LS circuit. LS circuit. So LS circuit is consist of what? Before the connecting to the capacitor to the inductor, so we need to charge it. Because so if the capacitor is not charged, so 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 this circuit doesn't mean nothing. It doesn't mean that nothing. Okay, that's why. So what? So wait, just wait. So what's going on here? So here is the positive terminal. This is negative plates. Yeah. So if I connect capacitor anything, and this capacitor has a charge, so it started flowing. So this is closed circuit. So the current flows from positive plate to the negative plate. Yeah. So this is current is flowing this direction. So but inductor is fights this against this current, because the inductor doesn't want to the through this, over this through the current. Okay. So this is why. So this inductor is produces magnetic field. So so changing the magnetic field is leads to the so generating the induced EMF. So in other words, so this here is the electric field. So the electric field energy is so 1/2 C V square, right? So we are converting electric energy to the magnetic energy. So the magnetic field energy, so magnetic energy is 1/Li square. Okay. So if you want to convert electric energy to magnetic energy, so you need to just LS circuit. Okay? Yeah, LC circuit. So here is, so we don't have any resistance. So ideal circuit, we don't lose any energy. So ideally, so it means that this energy is not damping. So you see here, or cosine or sine function. Yeah. So we don't lose energy here, but in reality we lose energy because of the resistance of these conductors. So we have already resistance here. So this is why the in reality the charge. So here is, you can see here, charge is decreasing or current. Yeah, the current decreasing by the time. Yeah. So this is damping the graph of the current in the circuit. Yeah, I mean in reality. So but so here is so so we don't have a external resistance. So any resistance. Okay. So this is why is the graph is so ideal. Yeah. Yeah. So we always have R, because any conductor has resistance. So so and so if I have a charge as a function of time is Q equals to the maximum value, capital Q cosine omega t, right? So Q equals to. So why I'm using here cosine, not sine? What do you think? So if I so if I substitute here, so if I want to find the charge at time is 0, so Q time is 0, so I need to substitute here T by 0, right? So it means Q times cosine 0, right? This is equals to what? 1. So that's why the current, so the charge initially was maximum value. So the omega times to the omega times to 0 is 0. Yeah. So the let me write here. So this is cosine phi and Q cosine omega t. So because phi is equals to omega t. Okay. Okay. So if I connect this capacitor to the inductor, so the capacitor starts to the discharging. Yeah. So it means that capacitor is the losing charge. So why? Because of the my electric field is converting to the magnetic field. So let me draw again the charge graph as a function of time. So here was the column, here was the second, yeah, and here was from the maximum value, and okay, this is the capital Q, right? So this is one period, yeah. So one period of time of oscillation, yeah. So so I'm not good at drawing. Thank you. So here is charge is zero, right? When? So time is when time is what? So this is so so period divided by 4. So quarter period of time. Why? So because here, so uh, this is one over 4, 1/4, and 1/4 is no. So this is the 1/4 and 1/4, 1/4, and 1/4. So how many 1/4s? 4. So overall we have t, yeah. So t over 4, t over 4, and t over 4, and t over 4. Yeah. So so 1/4. So after 1/4 of the period time is the charge reaches 0. So it means that current reaches the maximum value because current is equals to what? dq dt, right? And if I substitute here q by uh, this equation, yeah? Q cosine omega t, right? So what derivative of the cosine? Yeah, the q omega sine omega t, right? Minus. Okay, so this is maximum value of the current I max or I zero. Okay, and right here I max is equals to q times omega. Okay, so but the function is so current as a function of time is so they can be drawn by as a sine function here. So this is why. So the current flows from 0. So you see here, so from 0 to some, and so the value of the current is here uh, q times omega. Because here, so the minus q omega sine omega t. So derivative of the cosine is minus sine. So this is why. So the current starts from so the negative part of the current. Yeah. Any question? So let me express the uh, period of the time of this solution. It's equals to 2 pi ls. So this equation is formulated by Thomson. So this is why the Thomson equation. So the omega is, what's omega here? So what? This is frequency. So but angular frequency. Yeah. So what about the frequency? Do you remember relation between the frequency and the period? Yeah. So frequency, no. Capacitor stores the charge and energy, not voltage. So the voltage, so what? So when you charge the capacitor by connecting the power supply, so anyone. So this is the capacitor, yeah. So here is the voltage, yeah. This voltage equals to EMF of the power supply. It's constant anytime. If the so there is no charge, so the potential difference is equals to E. It doesn't change. We we just only here so storing charge. Charge produces so the electric energy. U qishnimi yig'maydi. Qara. Muvozanat deganda nimani nazarda tutyapsan? Hmm. Э, induktiv qaltakda qachonki o'zgaruvchan tok hosil bo'ladi, qachonki unga undan o'tayotgan magnit maydon o'zgarsa. Demak, unda har doim tok kuchi o'zgaruvchan bo'ladi. Mhm. Ha, plastinka bo'ladi. Ha, aha. Ha, qaltak o'zi nima uchun kerak? Magnit maydon hosil qilish uchun kerak. Elektr tok o'tkazasan, maydon hosil qiladi. Bo'ldi, vazifasi shu. Ha, maydon buni atrofida maydon hosil qiladi. So if you want to, if you need the magnetic field, so if you need the magnetic field, you can use the solenoid. You can use the inductor, not only to you don't need to the magnet bars. Okay. So do you have a magnet bars? I don't have, but I need the magnetic field. How can I get the magnetic field? What? So, do you know what the transformators? So, using the magnetic field, we decrease or increase the uh, voltage. So at home you have how many how much voltage you need? 220. So, but electric generator voltage, so the some kilowatts, yeah. So if you connect your cell phone or TV to this voltage, so you need to new one, yeah. So this is why we use transformer to reduce the voltage by what? By forming the magnetic field. Okay, we'll see that later. So magnetic field. Yes, that's why we need to the solenoids, inductors. So anything so that which produce magnetic field. Okay. So the frequency is so the 1 hour period. Yeah. So it means that 1 hour 4 pi 2 pi and times 1 hour ls, right? LT. So what about angular frequency? Angular frequency is 2 pi frequency. Yeah. This is 2 pi times 1 over 2 pi times 1 over LC. And what we have? So 1 over LC of root square. Yeah, this is angular frequency. So, so we know this equation here from. So, but here is the phi is inertial phase. Yeah. So yeah, phase. The phi is so you know the angle. Yeah. So in physics, we call this phase. Okay. Yeah. Inertial phase. Okay. Okay. Example here is so in LS circuit self inductance is uh, 2 times 10 to minus 2. So L is 2 times 10 to minus 2 Henry. And capacitance C is uh, 8 times 10 to minus 6 farad. Yeah. At time t is 0, and all of the energy is stored in capacitor. So it means that initially we store the capacitor with some charge and then connect to the inductor. So energy stored in capacitor which has a charge, so the charge, the maximum charge, yeah. So when time is 0, so we have maximum charge. That's why I'm using here the capital Q, yeah. 1.2 times 10 to minus 5 coulomb. And so what's the angular frequency of the oscillation in this circuit? So the omega, so this is the equation A. And B, what's the maximum current flowing through the circuit? So the B is I max. Yeah. So what about C? How long does it take to the capacitor become completely discharged? So it means that so the time to spend to the fully discharging the capacitor. So it means that times to take so the 1/4 of the period. Yeah, t equals to t divided the capital T divided by 4, and we need to find. Okay, any question? So the find equation of represents the Q. Yeah. So D is QT. Yeah. Okay. The first one, omega, is equals to 1 over root square LT. Yeah. And if I substitute here, so L by it was 2 times 10 to minus 2. L C is 8 times 10 to minus 6. And what we have? 1 over, so 16, 10 to minus 8. Yeah. And this is 1 over, so the 10 to minus 10 to 4 divided by 4. Yeah. So the omega is what? 2.5 10 to minus 10 to 3. So what unit? Rad per second. Okay. Yeah, because it's angular frequency. The frequency has so the unit second powered by -1, so or hertz. So question B. So this is A. Question B. So what was Imax? So the Imax Q omega. So what's Q here? 1.2 10 to minus 5 times 2.5 10 to 3. So the current is max is so 1.2 times so it's 1 over so 10 1.2 times 10 to divide by 4, right? It's 3, yeah? 3 times 10 to minus 2 ampere or 30 milliampere. It's maximum current, yeah? Yeah. So what about C? C is here. So the time, 1/4 period. Yeah. It's a period is here 2 pi. Let's see, yeah, and divide by 4. So T is pi. So L is where is it? So let me write here T by by omega, right? Time is equals to omega divided by 2 pi, yeah? And T divided by 4 is omega 2 pi 4, and what we have? Omega divided by, yeah, there. Sorry. 2 pi divided by omega, 2 pi divided by omega, and what we have? So pi divided by 2 omega, right? And this is 3.14 times, so divided by 2 times omega, where is it? Yeah, 2.5 10 to 4, yeah? And 3.14 divided by 5 or 10, so 2 pi, yeah? So I just multiplied both. So the denominator 2 and 10 to minus 4. Yeah, that's second. Yeah. So the time is equals to uh, 6.28 times 10 to minus 5 seconds. Am I right? Can you check? So 2 times 2.5 is 5. Yeah. And pi divided by 5, it's 2 pi divided by 10. Yeah. So this is 2 pi, and 10 to minus 4 divided by 10 is 10 to 5 minus 5. So what about the last one is q as a function of time? Q is a function of time is equals to capital Q cosine omega t, right? So I need to just substitute Q and omega. That's all. Q, so the capital Q is 1.210 to minus 5, and cosine, what's omega? 2.5 10 to 3 t, yeah? So, so the question here, write equation of the charge as a function of time. We don't know time. So if you want to find instant charge, so anytime you need to substitute t by so which value you want to find. Or we can write here the q t is equals to 12 cosine 2.5 10 to 3 is, and the unit is micro column. Okay, look at it. Yeah. So I just use it here. So the 12 10 to minus 6, it's micro. So the unit of the charge is column. That's why. So the I bring here this part is to the micro here column. So here is the column. Yeah. What? 2,5 nima? Yo bu argumentda turib buni chiqara olmaysan. Argument-ku bu. Cosine kx. Okay? So RLS series. So here as you can see the damping because of the resistance. Okay? So Mahmoud, here you can see this circuit RLC circuit. So you see here was damping. So reducing the charge by the time. And so the equation here for this circuit, so equation here L d squared q dt squared r plus. So dq dt, and so the plus 1 over cq is equals to 0, right? So this is damping equation of the charge. So we know this equation. From this equation, so that we can compute omega. So the charge is qt is equals to so e powered by r divided by rt divided by 2l cosine. So the angular frequency time t plus phi. So initial phase. So the omega prime here minus RT divided by 2L. So it's 1 over LC minus R 2L. So this is frequency. Frequency of, so angular frequency of RLC circuit. Yeah? So, the more detailed description will be the next chapter, yeah, of about the circuits. So there are, so we'll talk about impedance and so reactive resistance. So do you remember from circuit theory? So impedance and what? So we'll review. Okay. Okay. So can you solve this problem? Okay. So I will check it then. So the 201, yeah. Thank you. Yeah. No sir. No sir. Here. No man. Abror. This is the visa number. Visa number. It's from examples our textbook. So we have solution here. We'll check then. Okay. How to life. Javla. Diyor. Diyor. Dilshad. Mırşat. Rabbanaev. Nasiba. Muhlisa. Toshif. So energy is capital U. Yeah. So electric or magnetic energy? Which energy? So energy has dissipated in the resistor. So it's electric energy. Shahzad. Damped, it means that reducing the energy. Sonuçta yani damping. Ha. So is the circuit under damped, circuit damped and over damped? So the question is the circuit damped? No. So we have there was resistance. So here as you can see the damping graph. Damping of what charge? If the charge is damping, so the current is damping. I mean, so the current damping, so energy is damping. Yeah, because it depends. So, so why the because of the lose energy. So if you have a resistance, it means that so the electric energy so the transforms to the heat energy. Okay, this is the reason to damping. Karim Behrus, Abdullah Behrus, Mahmoud Yarf. Polvonzoda, Samardan, Samardan. Absent. Okay. Yeah. So what's the question here? So if the circuit starts oscillating with charge on capacitor, how much energy has been dissipated in the resistor by the time oscillation ceases? Why? Okay. What about time? Yeah. So so if you want to find energy, so dissipated energy, so you need just to use the 1 over 2, so Q divided by do you remember the capacitor energy by charge, and so what we have is capacitance q square divided by c, so that's all. So all energy we lose. Yo, sen topolmaydigan yo'l tanlading chunki vaqt kerak bo'lar sanga. Vaqtni bilmaymiz. So if you ask to find the angular frequency, you can use this equation. Must go to keys. What's keys? Mhm. Yeah. Yeah. I thought so. We need to find energy, dissipated energy, all dissipated energy. Ah, so I just looked. There's no time. That's why. So L is 5 times minus. So yeah, that's 10 to minus 8. R is 200. So multiplication of L and C is root square. Can you help him to computing this? undamped. So it's known from previous graph you see. So if you have in circuit resistance, it means that the current and charge is damped. It's always damped because of the heat energy. The electric energy transforms to the heat energy. So resistance has so it's mm, so I don't 2L 1 over LC minus R squared. Okay, so right here, so 2LC, 2L, just so 10 to minus 2. It's 4 times 10 to so okay. So 3 times 10 to minus 2 R 6, so 5 milli, and 2 times L, where's L? R, no, total. So it means that there is no oscillation. There is no oscillation. Yeah. So here is question for you: why there is no oscillation? What's problem in the circuit? So if I connect to the circuit uh, L and C and R, yeah. So R. What's problem here? C L R. So tomorrow you will explain what's the reason here in the circuit. Yeah. And tomorrow we'll have a practice class. Okay? We'll solve some problems. This. So that's all. Thank you. Bitta R yo'q. Mana resist sirkuit qildik-ku, sirkuit ichida faqat L bilan S ni tashkil etgan. Bitta endi LS, LC keyin R qo'shilganda shunaqa bo'lyapti. Ha. Damped or mana grafikka qaragin. Mana dampingda. Damping graph. Ha, damping bo'lyaptimi yo'qmi deganida. Savol. Aha. Finalgacha. Остановить запись. Endi. Bilmayman qayerga ketdi bu. У нас в следующее время активен. Все потоки записаны будет выключить. Вы уверены, хотите? Все потоки.